vacuum in full life cycle.
Thank you, Chairman. I feel so honored to be here to communicate with my academic questions and ideas. My topic is the effect of mechanical factors on creep and tip of stress current crackings. First, I want to introduce myself. My name is Cui Yinghao. I come from Xi'an University of Science and Technology. And my contents are including 4 parts. First is background and introduction. Second is fundamental element model. The third is results and discussion. And the last is summary and my future work. This part is a background and introduction. Figure 1 shows a schematic diagram of pressured water reactor power plant. In the red circle of Figure 1, there are lots of dissimilar weld joints, such as through pump weld joints, siphon weld joints, and wave tube weld joints, and so on. The particularity of the welding process makes the weld joints rigid, easy to occur stress current cracks. And as shown in Figure 3. In Figure 3, the base metal is stainless steel or nickel-based alloy, which is a strong anti-corrosion material, and its surface will form an oxide film. And the crack propagation process is a film rupture, electrochemical reaction, and a repetitive process at the tip of stress current crackings. As shown in Figure 5, is a schematic illustration of crack tip oxidation. From Figure 5, we can see that the oxide film rupture time occupies most of the crack propagation period. That's to say, oxide film rupture becomes the dominant factor of crack propagation. In Formula 1, we can see that for the answer put forward that crack tip strain lead to oxide film rupture. But crack tip strain is difficult to acquire. I would like to put forward creep-induced oxide film rupture and substitute crack tip creep for crack tip strain, as shown in Formula 2. As shown in Figure 4, shows the mechanical state at SCC crack tip, and the mechanical state affecting creep at tip is included 2 parts. One is external load, as shown in this place, and the other is film-induced stress. This paper discussed the main factors affecting creep rate and different crack lengths, and this part is a fundamental element model. As shown in Figure 6 is the geometric model of wet plate tensile specimen, and the wet plate width is 80 mm, and its length is 160 mm, and the crack length A is assumed as surface stretch 5 micrometer, 50 micrometer, 0.2 mm, 2 mm, and 10 mm respectively. In order to accurately creep at the crack tip, a measured path was defined nearby the crack tip. The following is the material model. The base metal is alloy 600, which is a poor hardening material, and the relationship between stress and strain can be described by unbound oscillation. And the oxide is chromium 2 oxide 3, which can generally simplified as a linear elastic material. The material parameter of alloy 600 and chromium 2 oxide 3 in primary water environment is shown in Table 1. Figure 7 shows the loading conditions of plate tensile specimen in the finite element model. The loading are divided into two parts. One is external load, namely film-induced stress, which is simulated by expansion in aqueous. The other is external load, shown in this place, and its value is 53 megapascal, which is calculated by the stress intensity factor K equal to 5 when correctness is 2 mm. Figure 8 shows mesh of global model and sum model under different calculations. This is the results and discussion. From figure 12 to figure 17 shows the creep and tip and film-induced stress and external load when correctness is surface stretch 5 mm, 50 mm, 2 mm, 0.2 mm, 2 mm, 10 mm, respectively. And in these figures, the black curve stands for creep produced by the film-induced stress, and the red curve stands for the creep produced by the external load. In figure 12, we can see that the creep produced by the film-induced stress is much larger than the creep produced by the external load. In figure 17 and figure 14, we can see that the creep produced by the film-induced stress is a little larger than the creep produced by the external load. In figure 15 to figure 17, we can see that the creep produced by the film-induced stress is more and more less than the creep produced by the external load. From the results and discussion, we can derive two conclusions. First is the creep at the SCC tip is an appropriate parameter in the investigation of crack growth, and accordingly the creep at tip increases will also lead to SCC crack growth rate increases. And second is the film-induced stress is the main crack driving force in the initial stage of SCC, while the working load is gradually becomes the main crack driving force as the SCC crack advances. And this is another important work is obtain of creep rate at tip. And this specimen is my creep specimen. Considering that the strain measured by displacement sensor includes the strain deformation of gauge section itself, the deformation of tension rod clamp, and the deformation of tension arc section and loading section. In order to obtain accurate creep rate of 306 stainless steel, the combination method of direct current potential drop, namely DCPD, and the strain gauge and the finite element analysis is used to derive creep at tip. And figure 19 to figure 22 show the equipment involved in this experiment. And figure 19 shows the high-speed stick strain gauge with LCD screen. 1920 shows the figure 20 shows the equipment of stress current equipment. Figure 21 shows the aqueous software and survey platform. And last, figure 22 shows the DCPD measurement system. And this is the experimental process at room temperature I have do. Figure 23 shows the experimental equipment of obtaining creep using strain gauge and DCPD in slow strain SCC testing machine. And this equipment includes three parts. One is DCPD measurement system, which is used to derive potential drop in gauge section. And Second is the gauge, the strain gauge, which is used to derive strain at the gauge section, at the gauge section. And the last is the slow tension equipment, which is used to make this specimen produce quick deformation. And this is the connecting lens of the specimen in DCPD systems. From the above experimental process, calibration relationship between potential drop at the gauge section and true strain of specimen at room temperature can be derived. And this part is my future work. And I want to repeat the same experimental process in high temperature. Under different stress and different temperature in autoclave to obtain the relationship between creep and time of 306 stainless steel. It is this typical curve, and then derive the creep law. And this is current equipment research conditions in our lab. Thank you for your time.